So I've divided up these videos into three parts because the chapter's kind of in three parts. The next thing that we're going to talk about is energy in the cell. And energy we're going to use as the molecule of ATP and understand a little bit more of ATP. In chapter 6, we're going to look at the process of cellular respiration. That is the chemical process that makes ATP. So that's the link between chapter 5 and 6. On a cellular level, remember that we started with like the teeny tiny and all those molecules. We're up to our cell biology now. On a cellular level, your cells are always busy and they're always doing work. It doesn't matter how tired you are, it doesn't matter how lazy you feel, it doesn't matter if you're asleep or not. On a cellular level, we have all kinds of things going on. If we think to that idea of cells being small units or factories, what's going on in the factories are thousands of chemical reactions. So the result of all those chemical reactions is really the metabolism or the maintenance of the cell. We need to make new cell parts, we need to divide the cells. Some chemical reactions release energies and some use it up. So in order to really understand the cell, we're going to start with a definition of energy. And if we haven't talked enough about chemistry in this biology course, we're actually going to talk a little bit about physics coming up. So energy, this is one of the poorest definitions, I think, in the world of science. Energy is generally the capacity to cause change or to perform work. The energy, it's the capacity to do work, oftentimes in physics. It's measured in joules. If you've ever taken a physics course or that sort of thing before, maybe in just another science course. And oftentimes we could talk about different kinds of energy. So we can identify different kinds of energy, even if our definition of what energy is a little bit funky. So, or general or vague, I'd say. So kinetic energy and potential energy are the two general kinds of energy when we talk about energy in science. And so everything to do with kinetic energy is about motion. And so if things are moving, so maybe movement is a better word for you. So if anything's moving, that is an example of kinetic energy. So if water moves through a turbine, it generates electricity. Even electricity flowing, electrons moving, is kinetic energy. The other one would be heat or thermal energy. And so on a molecular level, the hotter something is, the more the molecules are moving about. You can think of that with water. So in ice, the water molecules are locked into place. As it melts into liquid water, we've got more movement of those water molecules. And as it moves into steam, those water molecules are moving even faster. And so the hotter something is, the more energy it has. The opposite of this, so things that are not movement energy or energy of motion, would be energy that is stored. And so potential energy is that. We could talk about gravitational potential energy. And so if I stay with, the examples that we live around geographically here, being on the Kootenay Lake and Kootenay River, gravitational energy is the water being stored behind the dam. Chemical energy is a good example of that that's relevant in biology. And so when you eat your lunch, as you metabolize your food, you're taking the energy that was stored in the bonds of your food and releasing that for your cells to do work. And so chemical reactions all involve breaking bonds and making bonds. When you break a chemical bond, it releases that stored energy. So like when you digest your food. And so it was stored energy, it had potential energy before you released it. Okay, so a little bit more. If we were to understand energy a little bit more, we could talk about how that energy can't be created or destroyed, but it's always converted from one form to another. So we have that idea of a constant amount of energy in the universe. And so this holds with my my river analogy or my river idea, where we have that gravitational energy of the water stored behind the dam, and as it flows through the turbine, it's shifted from one form of energy to another. Now, nothing is 100% efficient, but that's what we're talking about. So you might think of, the energy in your lunch coming out in your actions as you walk to your job later today, right? And so there's always these different forms of energy, but we're never creating or destroying energy. The other thing that happens is that generally, the world tends towards chaos. And so what we're talking about here in terms of energy is entropy. And so entropy is the level of disorder. And so generally, things like to go downhill energetically, like I was talking about with that concentration gradient. And then it also, things tend towards chaos. It takes energy to put things from chaos back into order. And it doesn't take much for me to think about this. If I look at the state of my purse or the state of my car or the state of my kitchen at the end of the day, I know that it takes energy to put those things back in order. It's not my fault. The world tends towards chaos. It's just entropy. Okay, so if we were to talk about general kinds of chemical reactions and energy, we could talk about how things go downhill. So that would mean that energy is exiting. So remember, we can't create or destroy. If we have a high amount of energy stored in our reactants of a chemical reaction, and then after we have a low amount of energy in our products, that means that the energy is released out into the world. And so a good example of this would be burning wood in my wood stove. So I have lots of energy in those cellulose molecules of my wood. And then after, I'd have ash, I'd have carbon dioxide, I'd have H2O, and there's tiny amounts of energy stored in those little tiny molecules. And most of that energy is going to come out to heat my wood. Same thing goes for cellular respiration, the topic of chapter 6, which is up next. So chapter 6, or cellular respiration, also releases energy and heat. But its products can be released to perform work. And so the energy that's released in cellular respiration is also ATP. Let's take a look at the other one. So I should say here, exergonic. So exer is out, or it's exiting, out energy in that chemical reaction. So ergon is work or energy. The opposite of an exergonic reaction would be an endergonic reaction. Oh, sorry, I forgot about these. So these are the pictures. It could be combustion in your car, or it could be wood burning, or it could be cellular respiration. All of these have a high amount of energy, lots of potential energy here. So lots of potential energy and little potential energy. Energetically, they're going downhill and releasing energy out into the world. They're exergonic processes. Endergonic reactions also happen, and that means that energy has to go into a chemical reaction. So it requires an input of energy, and it makes products that have a lot of energy stored in them. The classic example of this would be photosynthesis. And so plants take water and carbon dioxide, and then the energy from the sun as an input to make the products, often carbohydrates. And so here we have a low amount of energy in my reactants and a high amount of energy in my products. And so this would be an endergonic reaction as the energy goes into the process. So our overall cell metabolism involves both endergonic and exergonic reactions. My cells don't have photosynthesis, but there are still chemical reactions going on in them that are endergonic, where they use up the energy of exergonic reactions. And so really what we're talking about here is keeping the cell alive, this cellular metabolism. The kinds of work that your cell does that it needs the energy for, it needs the ATP for, is energy coupling, so we need energy to drive those endergonic reactions in our cell. We might also have mechanical work, so cilia or flagella, if we have a cell that can move about. And then we also have transport work, so this was active transport. We needed ATP for those. So that's the kind of work that your cell is doing. To do this work, a cell has to manage its energy resources, and it does this by energy coupling. What I mean by energy coupling is that we have both exergonic and endergonic reactions, and they work hand in hand to make the cells work efficiently. And so it's all about efficiency and keeping the cell alive. So ATP is the molecule that does all of this work. ATP is the currency of the cell. So like the dollar is the currency in Canada, ATP is a molecule that we're talking about when we talk about any energy in the cell. So ATP is the carrier and storage unit of energy. It's like it's packaged so that it's useful for the cell. ATP stands for adenosine triphosphate. That means that there are 3 phosphate groups in a molecule. The source of making ATP is food. And then generally, if you were to kind of trace it back, the idea that we are consumers, we eat producers. And so the food originally came from the sun. So we could even step back, not just on a cellular level, but even the universe or the earth has energy coupling, right? So if we were to take a look at this molecule of ATP, there is a high amount of potential energy held in some of its bonds. And so there is a lot of energy held between the second and the third phosphate group. So this is ATP. It's adenine or adenosine, right? When you take in consideration the sugar. So this would be a nitrogenous base. This would be right here. This would be the sugar, ribose. And then, like I said, there are 3 phosphate groups. Now, this is the key bond in ATP. That bond has lots of potential energy. When we have hydrolysis, when that water molecule goes in, that allows one of those phosphate groups to pop off and releases all of that energy. So when we've done this, we've gone from ATP to ADP because there are 2 phosphate groups down here. It releases a phosphate group, but this is the key payout. This is the key thing that's supposed to be going on. That's what we're trying to get out of the ATP molecule. So ATP becomes ADP, and that idea that there's energy coupling is totally in this concept. So ATP becomes ADP because it's hydrolyzed, right? Remember, water goes in. And then we could add that phosphate group back on when we phosphorylate the ADP back to ATP. Remember, this has 3 phosphate groups and this has 2 phosphate groups. The key thing with this is that this process releases all of that energy, right? So that energy can be used to drive endergonic reactions. So this coupling, this recycling that happens between ATP and ADP is really what we're talking about with that energy coupling. The other side of it is that to put that phosphate group back on, we need energy. And so that energy comes from those exergonic reactions. The efficiency of this, even on a chemical level, it's a form and function thing. Like we've got such a tight cycle here that you actually don't even need that much ATP in your body because your body is constantly recycling it and renewing it.